We recognize the setup immediately. One person stands at the front of a crowded room, delivering information to dozens of people taking notes. Yet we often encounter a frustrating reality. A Nobel laureate or renowned historian can be entirely incapable of explaining their field to a beginner. It's tempting to blame this disconnect on the professor's intellect or the student's lack of discipline. The actual bottleneck is mechanical. We call it cognitive friction, a direct mismatch between the format in which an expert transmits data and the strict biological constraints governing how a human brain receives it. To survive a modern environment saturated with information, the human brain developed aggressive defensive filters. At the base of the brain sits the reticular activating system, or RAS. It functions as a strict gatekeeper. If incoming data is monotonous and highly predictable, the RAS flags it as spam and shuts down the connection. When a student loses focus or falls asleep during a droning presentation, they are not exhibiting a moral failure. Their brain is executing a successful physiological defense against cognitive overload. You have likely heard the claim that the human attention span has shrunk to just 8 seconds, worse than that of a goldfish. That statistic is a fabricated myth. This graph mapping neurological engagement shows the reality. Healthy adult attention does not flatline. Instead, it pulses in repeating waves, peaking and dipping every 10 to 15 minutes. To transfer knowledge successfully, we must stop forcing audiences into passive endurance tests. We have to engineer the delivery to match these biological pulses. In 1965, an educational psychologist named Robert Gagne developed the 9 events of instruction. Far from an outdated administrative checklist, this model is an operating system explicitly designed to hack our cognitive constraints. We can map Gagne's 9 snipes across 3 distinct biological phases of learning: input, processing, and output. Effective instruction requires a targeted biological intervention. This framework provides the precise algorithm needed to navigate information through the brain's heavily guarded pipeline. Phase 1 is input. Gagne's first step is to gain attention, which means the instructor must intentionally force the RAS gatekeeper to open. The brain is hardwired to let 4 specific variables bypass its filters: imminent threat, sudden novelty, high contrast, and extreme personal relevance. Instead of opening a physics lecture by writing equations on a chalkboard, you show the famous collapse of the Tacoma Narrows Bridge. Watching thousands of tons of concrete tear itself apart breaks the predictable pattern of a classroom. This triggers a microdose of dopamine, signaling to the brain that the upcoming information has high salience and might be necessary for survival. Once the channel is open, Gagne's second step is to inform objectives. The brain operates like a search engine. It requires precise parameters to scan effectively, rather than a vague chapter summary. We define this using the "what's in it for me" principle. Telling medical students we will review diagnostic protocols is weak. Telling them this specific method will help you differentiate a common cold from fatal meningitis instantly locks in their focus. Step 3 is stimulate recall. Before introducing a new concept, the instructor must verify that the structural foundation is already in place. Forcing the brain to retrieve prior knowledge groups separate pieces of information into cohesive blocks, or chunks. This dramatically reduces the cognitive effort required to process whatever comes next. Hacking the attention filter is useless if you do not immediately bind the new data to the listener's pre-existing neural architecture. Without that anchor, the system quickly overloads. Phase 2 is processing. Here, the instructor moves to step 4, present content. The single greatest risk at this stage is cognitive overload. Human working memory is severely limited. It can only hold and process roughly 4 to 5 distinct elements at any given time. This biological limit explains why reading text verbatim off a presentation slide is highly destructive to learning. This schematic illustrates what psychologists call the redundancy effect. When the eye reads a sentence on a screen and the ear hears the exact same sentence spoken aloud, the visual and auditory channels conflict, overriding each other and causing a bottleneck. To fix this, we apply dual coding theory. As the visual channel processes a geometric diagram, the auditory channel processes the spoken explanation. Because the formats are different, they run in parallel, doubling the brain's bandwidth.
Step 5 is provide guidance. We call this scaffolding. The expert must explicitly narrate their own internal logic, voicing the invisible decisions they make when analyzing a problem. A crucial part of scaffolding is establishing boundaries by showing both clear examples and precise counterexamples. If a professor wants to teach Baroque architecture, they show the heavy, ornate details characteristic of the style. Then, they immediately present a counterexample, showing the lighter, asymmetrical design of Rococo architecture to establish the exact variables that separate the two categories. By relying on dual coding and explicit scaffolding, we ensure that working memory isn't crushed by the sheer volume of data it just allowed inside. Phase 3 is output. This brings us to steps 6 and 7, elicit performance and provide feedback. Learning requires active generation. Passive listening creates a dangerous illusion of competence. The brain only retains what it actually produces. When a learner attempts a task, feedback must be formative and instant. It serves as a navigational recalibration, a quick course correction, rather than a delayed, punitive grade delivered weeks later. Step 8 is assess performance. This relies on frequent, low-stakes testing that strictly measures the exact objectives established at the beginning of the lesson. This utilizes the testing effect. The physical act of retrieving information from memory alters the brain's structure. As a neuron fires, the connective dendrite physically thickens, solidifying the pathway. Gagnet's 9th and final step is enhance retention and transfer. Educational psychologists consider this the ultimate metric of success. Transfer forces the brain to extract an abstract principle from a known problem and apply it to a completely unfamiliar context. A student achieves transfer when they can take the physics of architectural tension used to build bridges and apply it to understand human skeletal biomechanics. The educational cycle remains incomplete until knowledge is physically extracted from the vacuum of a lecture hall and forged into an adaptable cognitive tool. This diagram shows the complete 3-phase cognitive pipeline in action. When all 9 steps align, data flows efficiently from input to long-term storage without generating friction. The most common critique of Gagnet's model is its strict rigidity, treating instruction like a mechanical assembly line. This is where we apply the principles of andragogy, or adult learning. While this rigid scaffolding is mandatory for absolute beginners, advanced learners require autonomy and problem-based freedom to navigate their own paths. Despite being published in 1965, the framework maps exactly onto the modern era. The current trend of microlearning, breaking courses into 5 to 7-minute modular videos, is just a digital implementation of Gagnet's working memory constraints. Generative AI serves as a methodical assistant for this framework. An instructor can prompt an AI to instantly generate novel hooks, precise counterexamples, and low-stakes formative assessments tailored to Gagnet's parameters. To succeed today, an educator must abandon the identity of a sage transmitting data and adopt the role of an architect designing a biological experience. Understanding these constraints allows any learner to reverse engineer the model. You can intentionally seek out hooks, define strict objectives, and force yourself to actively generate answers when studying alone. True expertise is not defined by possessing vast amounts of knowledge. It is defined by respecting the precise, immutable biological reality of how the human brain actually acquires it.